if f of x is equal to x squared, find f prime of x using the limit definition.
Oh yeah, and it was expanded, but where I don't know where I went wrong was technically it would be x times h plus x times h, making it 2xh. Right?
Not quite. So let's do this. So if I was going to find the derivative of x squared using the limit definition, there's actually a couple different ways you can do this depending on how your teachers talk about it. But the way I would usually approach it would be to write it as the derivative f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Just starting with the limit definition. And then we're going to write, well, if f of x is x squared, then f of x plus h, still writing the limit every time. F of x plus h is going to be, instead of x squared, it's going to be x plus h squared. It's minus f of x, which is x squared, all divided by h. Certainly stop me if you have questions. So then x plus h squared is x plus h times x plus h. So when we write this out, in fact, we can write it out up here. X plus h times x plus h. If we FOIL that out, we're going to get x squared and then x times h. Oh, I think I misheard what you were saying before. H times x and h squared, which we usually write as x squared plus 2xh plus h squared.
Right.
So then we're going to get the following. The limit as h approaches 0 of x squared plus 2xh plus h squared minus x squared all over h. Now what? Right. As is typical, right? We expect the things that don't have h's in them to cancel out. So then we're left with the limit as h goes to 0 of 2xh plus h squared all over h. You can factor out an h from the top here, or you can just go straight to saying, I'm going to divide each thing by h. I'll show you the skip step in a second here. But if you just divide each thing by h, 2xh divided by h is 2x, h squared divided by h is h. If you prefer, you can also take the step of factoring out an h from the top, or dividing out an h like that, and then saying the h divided by h is just 1. Now we're almost done, but the last thing we have to do here is sub in 0 for h. So we get 2x plus 0, which is 2x. And that is the derivative of x squared.
You said you sub in 0 for h?
Right, well, what I should really say is, from this step to this step, I'm taking the limit. So when we read this, this says the limit as h approaches 0 of 2x plus h. Meaning we're really asking the question, what is 2x plus h getting closer and closer and closer to as h gets closer and closer to 0? Well, if h is getting really, really close to 0, then 2x plus h is getting really, really close to 2x plus 0, which is just 2x. The process is just plugging in 0 for h, but the thought process is, oh, we're saying, what is this getting close to as h is getting close to 0?
And then where did you get the 2xh in red on the third line?
So when I multiplied or FOILed this out, I have x times x times h times x, and h times h. So the x times h plus the h times x, those are really the same thing, right? It doesn't matter, at least with regular things, it doesn't matter what order you multiply them. So x times h really is h times x. And if you add something to itself, you have 2 of that thing.
What messed me up though was that he wrote what I thought was 2xh as 2x plus h. So I was like, that makes sense. But
So
that
it might so was it this function exactly?
x squared minus 2x.
Let's look at a slightly different example then, because that's probably I think I see what's happening here. So let's look at, so in fact we'll do a couple of these because we might as well talk more about the power rule today as well, because that's certainly something we should get down. So let's say my function was f not prime of x. I'll just write this. Find f prime of x using the definition for f of x equal to let's make it 3x squared. I see, plus 2x. So same situation. We're gonna find the limit as h approaches 0. I'm gonna skip writing the definition because we just wrote it. Come on in. We're gonna get, I lied, I'm not gonna skip. I was gonna skip the definition, but I just can't. It's always a good idea to write this first. If you're ever finding the derivative using the limit definition, it's good to let the reader know that you know what the definition is. And then, and when I say reader, I mean the grader. The person grading your work, they're like, oh, at least they knew what the definition was. Give them a point. And then, so now we have to be careful here. F of x plus h. I'm looking at my function f of x, and everywhere I see an x, what I'm actually going to do is everywhere I see an x, I'm just going to write the same thing with parentheses. I'm going to write 3 times parentheses squared plus 2 times parentheses. That's my f of x plus h. And now I'm going to plug in x plus h. That's my f of x plus h minus f of x, which is 3x squared plus 2x. And something that's really important here, I have to be subtracting all of f of x, meaning I need parentheses around that to make sure I distribute the minus sign correctly. Divided by h. What should happen is when we multiply things out, all the things that don't have an h in them should cancel out on top. Maybe it's also possible some of the things that do have h's will cancel out. That's allowed for some of the h things to cancel. Sometimes it happens, but all the not h things definitely should go away. So let's be careful here. With the limit as h goes to 0, x plus h squared. So, and this comes up often enough that you want to get it to the point where you're like, oh yeah, x plus h squared is just x squared plus 2xh plus h squared. Comes up so often. So we're going to get 3 times x squared plus 2xh plus h squared, and then we're going to distribute the 2 here and get plus 2x plus 2h. We're going to distribute the minus sign, minus 3x squared minus 2x all over h. At this juncture, the only thing I could really cancel is the 2x minus the 2x. 2x minus 2x is 0. I can't quite cancel the negative 3x squared yet with the 3x squared here because I still have to distribute this 3 to all the other terms as well. And it's kind of dangerous to cancel that and then forget to distribute the 3. So I'm going to first distribute the 3 with the limit as h goes to 0 of 3x squared plus 3 times 2xh is 6xh, 3 times h squared plus 2h minus 3x squared, all divided by h. The 3x squared minus 3x squared is 0. Everything left has an h in it, so we're happy. You see h's, we're happy. Happy start to the h. I like that. Just made it up right now. I know. Amazing. Limit as h goes to 0 I'm going to factor out 1h from all the terms on top. I've got a 6x plus 3h plus 2 divided by h. We finally get to say h divided by h is 1. We get rid of that bottom h, which is always the thing that's causing a problem. And we're going to get the limit as h goes to 0 of 6x plus 3h plus 2. And then in the final step, we have to plug in 0 for all the h's, which just leaves us with 6x plus 2. Which, if we were to have used the power rule and also the constant multiple rule and the addition rule, right, we can see, oh yeah, the power rule says the derivative here is just going to be 3 times 2x to the first plus 2 times 1x to the 0. Or in other words, 6x plus 2. But of course, right, we don't really do that here because we're not being asked about it. Questions about any of this? Cool. It's okay to have questions. Before we keep going in this direction, are there any other questions or comments or thoughts from the exam? Like if there's something you saw in the exam that you would like me to talk about, I'm happy to. Yeah, Erica.
Well, I want to see you go over some of the questions like from the exam.
Sure, yeah, totally. Yeah, that's totally fine. Yeah, no, yeah, that's, yeah. Once you've taken the exam, I'm happy to go over all you want.
and 5.
Sure, but you'll have to tell me what the question is.
Yeah.
Mhm.
Says carefully stretch after that x equals x squared minus 2. And then,
So one more time, it was what?
yeah, x squared minus 2.
Mm-hmm.
And then, like, denominator is x
Uh.
squared, minus x minus 2.
Cool. That look right?
Yeah.
X squared minus 2 over x squared minus x minus 2. It's gonna be kind of a pain to, so there's something about this particular graph that's gonna be not as lovely as something typical. And just to make sure, it's definitely x squared minus 2 over x squared minus x minus 2. Okay, so when I'm sketching any sort of graph, usually what I'm gonna look for are the intercepts and the asymptotes. Later on, we'll talk about relative extrema, but we're not there yet. So intercepts, first we're gonna do the y-intercept. How do we find the y-intercept? Set x equal to 0. We set x equal to 0. F of 0 is going to be 0 minus 2 over 0 minus 0 minus 2. And negative 2 divided by negative 2 is positive 1. So my y-intercept is going to be 0, 1. X-intercepts. We set y equal to 0. But really, when it comes down to a rational function, you're just going to be setting the numerator equal to 0. So this is the part that I was referring to that's going to be a little bit less nice than usual. If we set the numerator equal to 0 and solve for x, we're going to end up getting x squared equal to 2. X is going to be plus or minus the square root of 2. Which is, I mean, it's not terrible, but it's just we like having integers. That's not an integer. How much is the square root of 2 approximately? About 1 point something. It's about 1.4. Not that you should know all of them, but square root of 2 comes up often enough that you might want to kind of put that in your memory bank. Oh yeah, square root of 2 is about 1.4. So we're going to get two x-intercepts, the square root of 2 comma 0 and the negative square root of 2 comma 0. All right, we've dealt with the intercepts. Now let's take the asymptotes. For the vertical asymptote, we find, oh, you know what I should have done before I did any of this? I know it's not going to play a role here, but technically before you start graphing any sort of rational function, it's usually a good idea to factor the numerator and the denominator and make sure you don't have anything that cancels out, because that can't play a role here. It's definitely not going to happen here because the numerator isn't really factored in a nice way. You could factor the numerator as x minus root 2 times x plus root 2. I wouldn't. The denominator, if we set that equal to 0, that does factor as x minus 2 times x plus 1 equal to 0. So we're getting x equal to positive 2 and x equal to negative 1. And then if you're finding a horizontal asymptote, what kind of work are you expected to show? Are you expected to take the limit as x goes to infinity, or are you just expected to look at the degrees and the coefficients? Okay, so the degree on top and the degree on the bottom are both what? 2. Since they're the same, that means the degree is just the highest power of x in the numerator and the denominator. So degree is 2, degree is 2. So that means the horizontal asymptote is going to be y equal to what? 1. How am I getting 1? 1 over 1, not 2 over 2, right? I'm not dividing the degrees by each other. I'm dividing the coefficients by each other. Just want to make that super extra clear. I don't know why I circled that one. And I guess I don't love making a sign chart, but I guess you all might. So we can make a sign chart. So let's see what's going to go on our sign chart. On the sign chart, all the things that should go on the sign chart are all the x things. So every x-intercept and every x vertical asymptote. So I've got 2 and negative 1 and positive square root of 2 and negative square root of 2. So there's 4 things. The biggest thing is positive 2. The next biggest thing is positive square root of 2. The next biggest thing is negative 1. And the smallest thing, or the most negative thing, is negative root 2. Yeah. So here's where I probably actually would factor this to make it easy to fill out my sign chart. So I'm going to rewrite my function f of x. I am going to factor x squared minus 2 which does factor as x minus root 2 times x plus root 2. If someone asks you if x squared minus 2 factors, you could say yes or no and be correct. No, it doesn't factor in the usual nice way where the things are integers, but technically it does factor with using irrational numbers. Where something like x squared plus 2 would not factor without using imaginary numbers. On the bottom, we've got x minus 2 times x minus minus 1. Here's what I want you all to see. Every one of these factors has what power? An odd power. Power is odd. That means every time you go from one side of the next intercept or vertical asymptote to the other side, the sign's going to change. So if we figure out the sign here, pick a number bigger than 2, like 7. 7 minus root 2 is positive, 7 plus root 2 is positive, 7 minus 2 is positive, 7 plus 1 is positive, and all positive things multiplied or divided together is going to be positive. Then we're pretty confident that it's going to be positive, negative, positive, negative, positive. That's also really nice because I really don't want to find a number between the square root of 2 and 2. I mean, we could pick like 1.5. And 1.5 minus root 2 is positive, and 1.5 plus root 2 is positive, 1.5 minus 2 is negative, and 1.5 plus 1 is positive, and a positive times a positive times a negative times a positive is going to be negative. But wow, that's way more work than I want to do. It's so much faster to be like, I can see that the sign is what? So the power is odd, so the sign's going to change. The power this came from is odd, sign's going to change. This came from there, power is odd, sign's going to change. That came from there, power is odd, sign's going to change. When I'm making my sign chart, I kind of like to just use my sign chart to make my graph. So I know I have vertical asymptotes at +2 and -1. And I have intercepts at negative root 2 and positive root 2. So I'm like, okay, my graph is above the x-axis. And then it's going to be below, and then down, down, down. And then on the other side, above. And then hit my intercept and below. And then on the other side, above. So you can kind of even use your, if you make this sign chart, you can use it to help you draw the graph. Now we should still draw the graph nicely, but it's kind of, I'm like, I know what I'm going to do. The only thing I didn't really include on this graph was my horizontal asymptote. Let's draw it. I think I can fit it in here. I also didn't include my y-intercept. So let's draw all the nice things. So my y-intercept is 1. My x-intercepts are positive root 2, which is about like right there. And negative root 2, which is about right there. A little more than 1, a little less than -1. And then we've got x equal to 2 is my vertical asymptote. And x equal to -1 is my vertical asymptote. And then my horizontal asymptote. Oh, check this out. The graph is going to cross the horizontal asymptote. Is that allowed? I mean, clearly it must be. The graph is going to do it. It's totally allowed. You can cross the horizontal asymptote as many times as you want or need to. In fact, you can cross a horizontal asymptote an infinite number of times. It just says that all the horizontal asymptote says is as you go way, way, way out to the right or way, way, way out to the left, the graph gets closer and closer to that particular y value. But it doesn't say anything about whether or not you're allowed to cross it. And just as a counterpoint, I'm trying to kill myself over here. You cannot cross a vertical asymptote. That's a totally different thing. You can't have the graph go like that. That's not what that means. So you can cross horizontals, you cannot cross verticals really. So let's see. So I'm just going to follow my graph here. So I'm going to do this. I'm going to come down this way. And then I'm going to go down, 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 down. On the other side here, I'm up. I'm going to make sure I hit this y-intercept. I'm going to come over and hit this x-intercept and then cross into the negative territory. On the other side here, I'm going to be positive again. And then I just stay positive, but I get closer and closer to my horizontal asymptote. Y'all might have converted me. The sign charts are pretty useful. I'm not gonna lie, they're kind of great. Questions about anything I said about this graph? Really wish I could. Oh, that's fine. Something I would point out, because I've seen this many, many times, is if your intercepts have odd powers, so I should say if the intercepts came from factors with odd powers, that means your graph is going to cross the x-axis. at those intercepts. Or if the powers were even, the graph would bounce off the x-axis. Similarly, the asymptotes came from factors with odd powers. That means they are opposite directions on either side of the asymptote. One side of each asymptote is going up, one side's going down. If they were even powers, both sides would go up or both sides would go down. It's worth that. All right, let's look at, you said also 5?
Yeah.
What's 5? There we go.
5 was. Using. I need to read that honestly. Yeah.
I can try.
Using the power rule.
Power something rule,
Okay.
methods of 2.2.
Tell me-
Differentiate
Let me take it.
Power rule. Why?
Okay.
Well, there's nothing about the power on the text there.
Using the power rule / sum rule. I don't know what to say about that then.
Let me see. Oh, then we have this one now. I think, by definition, find the derivative of f of x equals x squared minus 2x.
So we did, so I will say you kind of might have missed that one. We definitely did one like that a little bit before we came to class. But let's continue in that vein because I would like us to talk a little bit more about the power rule and some other stuff too today. So not that I won't entertain other questions from the exam. If you have them, feel free to ask them, but I'm going to talk about the power rule for a little bit. So let's talk about the power rule, which I know we already kind of talked about last time, but I really would like to just show you quickly kind of how we get the power rule. So let's say our function was x cubed. We wanted to find the derivative. Well, my derivative is going to be the limit as h goes to 0 of f of x plus h minus f of x all over h, which is going to be the limit as h goes to 0 of x plus h cubed minus x cubed all over h. And it sure would be nice if x plus h cubed was equal to x cubed plus h cubed and there weren't any terms in the middle, but it's not true. Right? X plus h cubed, and you multiply that out, you're going to get 4 terms. In fact, whenever you multiply out x plus h to a power, you're going to get that power plus 1 number of terms. So if we were to do like x plus h to the 5th, there would be 6 terms when you multiply it all out. I've seen this one enough times that I've memorized it. I know that x plus h cubed, don't worry, we're going to talk about how you get it, is x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed all over h. Okay, what did I do to do that? What famous triangle did I use to get that? Pascal's triangle. So I remind everybody, Pascal's triangle over here. I used the row where the second term was a 3. And really, when you draw Pascal's triangle, you should think of the top row as the 0th row. The next row is the first row. The next row is the second row. The next row is the third row, and so on. So I used the third row of Pascal's triangle for x plus h to the third. And I got 1 times x cubed plus 3 times x squared h plus 3 times xh squared plus 1 times h cubed. So the 1, 3, 3, 1 give me the coefficients. And then we just let the powers of x decrease 1 every time. The powers of h increase 1 every time. And that pattern always works. So we're going to do it a couple more times just to see that it really does work. But here, the usual thing happens. The x cubed and the minus x cubed cancel out. Everything left has an h in it. So I'm going to factor out an h. I've got a 3x squared plus 3xh plus h squared. H divided by h is 1. So then I'm left with the limit as h goes to 0 of 3x squared plus 3x times h plus h squared. And when I plug in the 0 for all the remaining h's, that's going to be 0 and that's going to be 0. So I'm just going to get 3x squared. or 3 times x to the 3 minus 1. You're thinking about it in terms of the power rule. This pattern happens every time. Yeah, we can fit the next one in here. Let's say we want to do the same thing for f of x equal to x to the 4th. So let's check it out. Our derivative using the limit definition, and I know we're going to get sick of this limit definition. We're probably already sick of the limit definition, but bear with me. You know, I will say, kind of. Later on, when we start talking about like a different function where you haven't already seen a rule for it, usually we go back. We're like, well, I don't have to take the derivative of this, so go back to the definition and try and use the definition to take the derivative. For this one, it's going to be x plus h to the 4th minus x to the 4th over h. And I think I would like all of you to try on your own right now to write out the 5 terms of x plus h to the 4th. It's going to be 1 times x to the 4th plus a few more things, and then you'll have a minus x to the 4th at the very end, all over h. But use this 4th row of Pascal's triangle to get your coefficients. And we know that the powers of x should go down by 1 every term, and the powers of h should go up by 1 every term. Ready? All right. I guess I can walk around and look at what you were writing. Cool. Yeah, yeah. And then it should be all divided by 8, right? Looking good, yeah. You want to look over there? You're gonna want like an x to the 4th. And then the next one's gonna be plus 4x cubed times h. We're using the 4 here to give us the next coefficient. And then the power of x is 1 less. The power of h is 1 more. What's my next coefficient going to be? What's my power of x going to be? What's my power of h going to be? And then 4 times x to the 1st times h cubed plus 1 times h to the 4th. You could do this the long way. You could actually multiply out x plus h times x plus h times x plus h times x plus h. Right? I don't want to, but you could. If you actually had to do this the long way, it kind of sucks, but it's not that bad. We know that that's x squared plus 2xh plus h squared. That is also x squared plus 2xh plus h squared. And then if you superfoil this out, okay, this. So you've got x to the 4th plus 2x cubed h plus x squared h. And then, okay, this. You've got 2xh times x squared is 2x cubed h. 2xh times 2xh is 4x squared h squared. 2xh times h squared is 2xh cubed. Plus finally the h squared times each thing. X squared h squared x squared. Order doesn't matter. H squared times 2xh. And finally, h squared times h squared is h to the 4th. Okay, let's see what I've got. I've got x to the 4th plus 2x cubed h plus a 2x cubed h is a 4x cubed h plus, am I missing? So right here, I blew it a little bit. That should have been an x squared times h squared, not an x squared times h. Sorry about that. X squared h squared, 4x squared h squared. Another x squared h squared for 6x squared h squared. I think I also made an error here. That should have been a 2xh times h squared, which is a 2xh cubed. Sorry, I was going too fast. And then we have a 2xh cubed plus a 2xh cubed, which is a 4x. See how terrible it is doing it the long way? But it is the same, right? We end up with the same thing. It just takes a lot more time. So you can do it the long way if that's more comfortable for you. But the point of this is that you can also do it using Pascal triangle to make it really much easier to expand this x plus h to the whateverth power. So looking back here, we do the usual thing. Now here's what I want you to see about this. These are always going to cancel. You're going to be left with something where you have the first term with h to the first, and all the later terms have a higher power of h. So that when we then factor out an h from the top, we get a 4x cubed or a something without an h in it. And then everything left is going to have at least one h in it. I get 6x squared h plus 4x h squared plus h to the third, all divided by h. These h's divided to 1. And then when we take the limit here, the limit as h goes to 0 of this one thing that doesn't have an h in it, plus all these other things that do have h's in them, well, all those just get to become 0. 0 times this plus 0 times this plus 0 is just going to be, all that's going to be a big old 0. So we're going to get 4x cubed. That's why this always ends up being the power you had moving down times x to the 1 less power, because that's always going to be the second term of your expression. Your old power times x to the 1 less power times h to the 1 more power. Questions before I do one more like this? One more that's going to give us the power rule. All right. So, no, we can't. Sure. So we keep looking at Pascal's triangle for just 1 second. Pascal's triangle 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10. Okay, fine. What I want you to really see is that if I go, so this is my 0th row, my first row, my second row, my third row, and so on. If I was going to go down to the pth row, the first thing is going to be 1. What's the next thing going to be? Well, let's see. In the second row, the next thing is 2. In the third row, the second thing is 3. In the fourth row, the second thing is 4. In the fifth row, the second thing is 5. In the sixth row, the second thing is going to be. So in the pth row, the second thing is going to be p. And you got a bunch of other stuff. I don't care what those are. And then I will say, bless you, the last two things are going to also be p and 1, right? Because there is symmetry here for Pascal's triangle, right? 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. It's always the same for the same things as the same last, the same first things as the same last thing. And maybe there's a middle term that doesn't get repeated. So if I write out what x plus h to the pth power is, I know my first thing is going to be x to the p. My next coefficient is going to be, instead of 1, it's going to be p times x to the 1 less power times h to the 1 more power. Oh, that's the product rule right there. Well, let's continue on. The next thing is going to be, I don't know what the next coefficient is. I don't really care. I'm just going to call it C2. And I'm going to get x to the p minus 2 times h squared. Plus a bunch of other terms. The second to last one is going to be p times x times h to the p minus 1. And finally, the very last one is going to be h to the pth power. I don't really care about anything after these first two terms, though. So now let's find the derivative of x to the p, which we already know is going to be p times x to the p minus 1. But we're going to show it using the limit definition. Things are going to get a little bit ugly here, but that's okay. We're going to have x plus h to the pth power minus x to the pth power all over h. But then we're going to replace this x plus h to the p with this long expanded version of it. So here we're going to get the limit as h goes to 0 of all this garbage. So x to the p plus p times x to the p minus 1 times h plus something times x to the p minus 2 times h squared plus a bunch of other terms that have one less power of x times one more power of h, all the way to the very last two, which is p times x to the first times h to the p minus 1 plus h to the p minus x to the p all over h. And just like every other time, what cancels? The x to the whatever. And just like every other time, everything left has an h in it. So we factor out an h, and we're going to get the limit as h goes to 0 of h times. Okay, so when you factor out an h, you're just dividing by h or reducing the power of h by 1. So I'm going to get p times x to the p minus 1 times, there aren't going to be any h's left over because I pulled out the one h that was there, plus some constant times x to the p minus 2 times h to the what? If I'm dividing out h, I'm going to have an h to the 1. Because if you distribute this back through, h times h to the first is h to the second. Bunch of other terms with higher powers of h. And then finally, the last couple terms are going to be p times x to the first times h to the what? P minus 2. It's one less than it was. Again, if you think about it, if you multiply this h by h to the p minus 2, we add the powers, and 1 plus p minus 2 is p minus 1. And finally, this last one here is going to be h to the p minus 1. All divided by h. And I think I left myself enough room here. H divided by h is 1. And then we're going to rewrite this as the limit as h goes to 0 of p times x to the p minus 1. The only thing that doesn't have any h's in it, plus all these other terms that have either h to the first, or the next one would be h to the second, or h to the third, plus all the way to h to the p minus 2 plus h to the p minus 1. Sorry, p times x times h to the p minus 2. And then that's going to go to 0. That's going to go to 0. All those things are going to go to 0, and you're just left with the power rule. P times x to the p minus 1. So a couple things to say here. Technically, we have only shown this is true for a positive integer power p. Because this Pascal's triangle trick only works if you have something like x plus h squared, x plus h cubed, x plus h to a nice positive integer number. But the power rule is true for any real number. So no matter what power you've got, x, the derivative of x to a power is always that power times x to the one less power. So for example, if my function were to be, say, like x to the, sure, let's do something weird like x to the, nothing, I think something weird, sure, x to the negative fifth. Even though we didn't show that this power rule was true for negative powers, it is true for negative powers. And the derivative here is going to be negative 5 times x to the negative 5 minus 1. It's never a bad idea to write it out like this. Yeah, we can do the subtraction in our heads, but if you feel like you might be making a mistake easily, write it out the long way. And then we're going to, oh yeah, negative 5 minus 1 is negative 6. The power rule, you definitely want to feel it in your soul. The power rule, you're gonna use the power rule all the time from now on, right? It's gonna just like there isn't gonna be a day where you're like, oh, do I not know the power? You know, every day the power rule is probably gonna come up. Whether you're also using the product rule or the quotient rule or the chain rule, which I know are rules we haven't talked about yet, but it's certainly gonna come up in examples like that. So let's do a few examples here. Let's say our function g of x was equal to, yeah, let's make it fun. Let's say it's x to the 6th plus 2x to the 4th minus 3x squared plus 2 times the square root of x, all divided by x to the 3rd. I want to find the derivative of that. And we don't know the quotient rule yet. And even if we did know the quotient rule, you wouldn't use it here because it would be terrible. Instead, and this is generally true, we should simplify this expression before taking the derivative. And that is usually a good rule of thumb. If something is easy to simplify before differentiating it, it is usually a good idea to do so. So I'm going to divide each thing in the numerator by the denominator. I'm going to rewrite this as g of x equal to x to the 6th divided by x cubed. Notice I didn't write g prime. I know I'm trying to find g prime, but I'm not finding it yet. All I'm doing is simplifying, which means it's still the same thing I already started with. The reason I mention this is because I see a lot of people sometimes be like, oh, I'm finding g prime, but no, we're not yet. 2x to the 4th over x cubed minus 3x squared over x cubed. Now let's make our lives easier. Let's write this as 2x to the 1/2 over x cubed. If you're comfortable, you can totally skip this step and just do the division, which is totally fine. So g of x is going to be x to the 6th divided by x cubed is x to the 3rd because we're subtracting those powers. 6 minus 3 is 3. 4 minus 3 is 1, so you get 2x to the 1st. 2 minus 3 is -1, so we get minus 3x to the -1. And 1/2 minus 3 is 1/2 minus 3 over 1, which is 1/2 minus 6 over 2, which is -5/2. So you get 2x to the -5/2. And now we're ready to take the derivative, right? All we've done so far is simplify. Now let's differentiate using everyone's favorite, the power rule. So the derivative of x cubed is 3 times x to the 3 minus 2. I don't love using the power rule for 2x. I mean, you can, but really we should see that when you have a line like y equals 2x, let me ask everybody, for the line y equals 2x, let me draw it over here, y equals 2x. What's the slope of that line? Does it matter what point you pick? No, the slope is always 2. And one way to think about the derivative is the slope of the tangent line. But really, for any point here, the tangent line is just the line. So what I should really be saying is more broadly here, for a straight line with some slope, the derivative of that straight line is just the slope of that straight line, or the rate of change of that straight line. So the derivative of 2x is just 2. You could also use the power rule, right? There's a 1 there. The 1 could come down, 2 times 1 times x to the 0. Anything to the 0 is 1. So it would also work that way, but it's just better to be like, I know it's a straight line. I know its slope is 2. I know its derivative is 2. Here, the -1 comes down. -3 times -1 is +3. X to the -1 minus 1 is -2. And finally, the -5/2 comes down. 2 times -5/2 is -5. And then we get x to the -5/2 minus 1 is -7/2. Yeah, let's look at another here. So rule of thumb so far is if you can simplify the expression before differentiating, we probably should. Let's look at another example. Yeah. Sorry, I'm a little faster. So let's say we have this function. F of x is x to the 4th plus x to the -1 times 2x cubed minus x to the 2nd. Yeah, sure, that's fine. And I want to take the derivative. And we don't have the product rule yet. And even if we did, probably still would use it. Because this is easy enough to simplify before differentiating. So again, I want to find f prime of x, but first I'm going to simplify my function by just multiplying it out. In fact, I want you all to multiply it out. So FOIL that out and see what you get. Think about where I need to go. Yeah. Do that times. Okay, good. Oh, maybe I might, yeah, sometimes I make errors. Thank you, thank you, thank you. There, it's a really big minus sign. So if you multiply this out and you pay attention to the work you're doing, you should get 2x to the 7th minus x to the 6th plus 2x squared minus x, or x to the first. So let's now find the derivative. So our derivative, just using the power, well, okay, so technically I'm using like 3 rules here. I'm really using the power rule. I'm also using the constant multiple rule, which means if you have a function times a constant, that constant just gets to stick around. And I'm also using the addition and sum rule for derivatives, where if you have a bunch of things added or subtracted together, we just differentiate each of them and add or subtract. We've been using these rules already. We never really talk about using them, except for right now. So the derivative of 2x to the 7th is right, but I'm going to write it as 2 times 7x to the 6th, just to really emphasize the constant multiple rule here. The constant hangs out, and the derivative of x to the 7th is 7x to the 6th. Minus the derivative of x to the 6th is 6x to the 5th. Plus the derivative of 2 times x squared is 2 times 2x. And what's the derivative of x to the first? 1. Right? Because it's the line y equals x, and its derivative is the slope of y equals x, which is just 1. Or if you want to think of it as negative x, it's negative 1. And of course, you should really just skip this step and write my derivative as what you all were saying, 14x to the 6th minus 6x to the 5th plus 4x minus 1. Okay, couple more, and then yeah, then we're gonna change gears. Let's say we have this function. Let's say g of x is equal to, sure, we'll try this. I don't know why I wrote g of x there. One example, sorry. So g of x is going to be, sure, 4x to the 9th plus 2 over the cube root of x plus 5x plus pi to the 6th power. And I want you all to find the derivative. But before you all find the derivative, you should make one simplification. You should write 2 over the cube root of x as 2 times x to what power? Almost, it would be 2 over x to the 1/3. It'd be 2 times x to the negative 1/3. So if you make that simplification, now you're good to go ahead and take the derivative. So go ahead and find g prime of x, showing as much or as little work as you wish. Like that. Just as an FYI, I won't be here tomorrow. I know we don't have class tomorrow, but it's like if you're looking for me in office hours tomorrow, I will not be on campus tomorrow. So the normal office hours I would have from 10 to 11, actually, it's the 1 office hour tomorrow in C class tomorrow. I will not be there tomorrow, so don't look for me tomorrow. I won't be around. I'm going to lovely Wairika, everyone's favorite place. My family lives there. Not from there, they moved there from Eureka, which is not that far, but you know, whatever. Okay, so derivative of 4x to the 9th is 36x to the 8th. Nothing against Wairika, by the way. It's a perfectly fine place. Just I don't know. I wouldn't have wanted to grow up there, I suppose. So anyway, little 2 Jefferson, part of California for me. Anyway, not to be political. 2 times derivative of x to the negative 1/3 is negative 1/3 x to the negative 1/3 minus 1 is negative 4/3. I should have written that as just negative 2/3 times it, but I didn't. Derivative of 5x is 5. Derivative of pi to the 6 is not 6 pi to the 6 minus 1. Pi to the 6, if you plug pi to the 6 in your calculator, you're going to get a number that never changes. Also known as a constant. And constants have what kind of derivative? 0. So if something doesn't change, or better said, if something doesn't have a variable in it, that there's no x's there, and it's definitely meant to be tricky, right? I wrote that on purpose to try to trick you. That thing there is derivative is 0 because it never changes. In a similar way, e to the 6th, derivative is 0. E to the x is a totally different animal. That thing has a derivative that we haven't talked about yet. But if you don't see any variables, meaning typically x, but it could be whatever other letter someone has chosen to use. If you don't see that variable, that thing's a constant and its derivative is 0. And then I suppose I would write this as 36x to the 8th minus 2/3 x to the negative 4/3 plus 5. Sorry, my 3 down there looks terrible, but you all know it's 3. Cool. Okay, one more thing before we do the new thing. Everything's always a new thing. Where'd my example go? Let's do the following. Yeah, let's find the equation of the line tangent to, what do I got here? Sure. F of x equal to the square root of x times x plus 6 at x equal to 4. I'm sure you've seen some tangent line problems already. But just as a reminder, whenever you're trying to find the equation of a line, I don't care if it's a tangent line or just any old line, we need 2 things. We need a point, so an x comma y, and a slope, so an m. They already gave us the x coordinates. To find the y coordinate, we're going to plug that into the original function. So our point, x comma y, is going to be, well, the x value is what? 4. And the y value, I could very generically write that it's going to be f of 4. I'm just going to take that 4 and plug it into my function. Now, I should actually do it. But that you could, like, if you weren't sure, you just were writing something down fast, that would be totally like, you're at least demonstrating, oh, I know what I'm supposed to do here. I know I'm supposed to have an x and a y value. So let's see, f of 4 is going to be the square root of 4, which is right over. F of 4 is the square root of 4 times 4 plus 6, which is 2 times 10, which is 20. So that's my point of tangency. So whatever this graph looks like, I don't really know what it looks like. If I pretend it looks something like that, and over here, here's my point, 4 comma 20, I'm trying to find the equation of this tangent line. Wow, tangent line, sure, yeah, we'll pretend that looks like a tangent line. So we've got the point, we need the slope. And it's calculus. Whenever someone says it's calculus, and then do a thing, they mean we're using derivatives. That's right, like what is it? There's calculus, how do we find the slope? It means we use a derivative to find the slope. So to find the slope here, we're going to find the derivative, f prime of x, and then we're going to plug in 4. So I really, I should have, I'm bad news here. I got ahead of myself. I don't know how to take the derivative of this yet. I have to multiply it out. So before I can find f prime of x, I need to simplify f of x. F of x is the square root of x, which we want to write as x to the 1/2. Almost always, if you know you're going to be taking a derivative, it is better to write a square root as x to the 1/2, a cube root as x to the 1/3, any sort of root as x to the 1 over that root power. So this is, if I distribute, x to the 1/2 times x to the 1 is x to the 1/2 plus 1, which is 3/2, or if you prefer, you could write 1.5, but we usually like fractions as our powers. And then x to the 1/2 times 6 is just 6 times x to the 1/2. And now we're ready to take the derivative. The derivative is going to be 3/2 times x to the 3/2 minus 1 is 1/2, plus 6 times 1/2 is 3, and then 1/2 minus 1 is our new power is negative 1/2. And now if I'm gonna plug in 4, I might actually rewrite it with square roots. Because to me, it's easier to think of the square root of 4 instead of 4 to the 1/2. So if you really wanted to, you can rewrite this as f prime of x is equal to 3/2 times the square root of x plus 3 divided by x to the positive 1/2, which would be 3 divided by the square root of x. And now I can plug in 4. I mean, I could have plugged in 4 before. And get 3/2 times the square root of 4 plus 3 divided by the square root of 4, which is going to be 3/2 times 2 plus 3 over 2. Those twos cancel. And 3 plus 3/2 is 3 plus 1.5, so 4.5 or 9 over 2, if you prefer. And I left myself no room to write my equation. I got some over here, I guess. So here's the deal. Once you have your slope and your point, the equation of the line is very straightforward. It's just a formula. It's people write this like 3 different ways. I usually write it as y minus y1 equals your slope times x minus x1. But some people use y naught and x naught, or f of a and a, depending on how they're writing it. It's the same idea. It's y minus your y coordinate equal to your slope times x minus your x coordinate. But the y there and the x there just stay as y and x. Those are the things we need to write the equation in the line. So in this example, we're going to have y minus 20 equal to my slope 9/2 times x minus 4. And if no one says you have to do anything else, you could leave it like this. Often people expect you to write this in the more standard form, y equals mx plus b. So I would distribute the 9/2 and say y minus 20 equals 9/2 times x. And 9/2 times 4 is 36 over 2, which is 18, so minus 18. And then I would add 20 to both sides to get y equal to 9/2 x. And negative 18 plus 20 is plus 2. That would be the more standard way of writing the equation there. But certainly not incorrect to write it this first way if no one says to write it in a specific way. Both of these are the same equation of the same line, but it's written different ways. Cool. So now I was looking at Tabernetti stuff mostly. I was looking at the last lecture notes before midterm where he talked about trigonometry. So trig is definitely something we do need to be aware of. You are kind of expected to know how to evaluate sine, cosine, tangent, secant, cosecant, cotangent at various angles. Maybe know what their graphs look like. I want to start with what the graphs of sine and cosine look like, because that is where, well, that's kind of what we need to do, what we're going to do moving. There are other things, and we can certainly circle back around, but let's start there. And well, maybe not quite there. Let's start here, actually. Let's start with the unit circle. Everyone's favorite. Okay, let's start with an abbreviated unit circle. I mean, I'm not gonna I don't want to draw the unit circle with all 16 angles and all the points on the unit circle. Here's the unit circle I want you to draw when you're drawing the unit circle. Wow, first try to draw a circle. And then I'm going to label what I call, my wife hates this, but I'll do it anyway, the 4 corners of the unit circle. He's like, okay, circles don't have corners, I know. But it's easier than saying the 4 cardinal directions of the unit circle, or the north, south, east, and west points of the unit circle. So I'm going to say the 4 corners of the circle. And it's called a unit circle because it has a radius of 1. So if you go 1 to the right, that point is 1, 0. If you go 1 up, 0, 1. 1 to the left, -1, 0. 1 down, 0, -1. And the corresponding angles are, so going to the right, or the positive x-axis, that angle is 0. So the angle here is 0 radians or 0 degrees. Typically, we try to use radians though, because, well, that's how we're going to graph things. If I go up to the top, I've gone how many degrees? 90 degrees. I've gone the right angle. So up here, my angle is 90 degrees or pi over 2 radians. If I go halfway around the circle, my angle is 180 degrees or pi radians. And finally, 3/4 of the way around the circle, my angle is 3 pi over 2 or 270 degrees. And finally, if you make a full revolution, you get theta being 2 pi radians or 360 degrees. The reason I've labeled these points specifically, well, actually, I should let me talk about the. Oh wow, that's gross. I should talk about here is that the whole idea with the unit circle is that if you go some angle, let's use difficult here. If I go some angle measured from the positive x-axis in the counterclockwise direction, that angle, if I call it theta, let me draw a perpendicular here. So drop a perpendicular. I'm going to call this base of my triangle x because I've gone over x, and this height of my triangle y. So this coordinate on the unit circle is the point over x up y. But now, oh, and what's the radius of my circle again? What is the radius of my circle? Yeah, it's 1. Right, so that is why it's called the unit circle, because 1 is the unit. That's why it's called the unit circle. So using right triangle trigonometry, everyone's favorite SOHCAHTOA, if I look at sine of theta is the opposite over the hypotenuse, which in this case is y divided by 1. But y divided by 1 is just y. So y is equal to sine of theta. And similarly, cosine of theta is equal to the adjacent over the hypotenuse, which in this case is just the x divided by 1, which is just x. So x is equal to cosine of theta. So the point of the unit circle really is that this coordinate on the unit circle is always equal to the x coordinate is always just cosine of whatever your angle was, and the y coordinate is sine of whatever your angle was. It's kind of neat. What we can do with this is then say, okay, well, great, I can use these points on the unit circle to find something like sine of 3 pi over 2. Well, if I go all the way around to 3 pi over 2, the x coordinate is 0, the y coordinate is -1, so sine of 3 pi over 2 must be -1. And cosine of 3 pi over 2 must be 0. That is one of the many uses of the unit circle. Yeah. And I'm just trying to, there's a lot of things to say about trigonometry, but I'm not trying to say too much. So what I want to do with the unit circle is now use it to graph sine and cosine. So I want to graph, let's start with sine. Y equal to sine of x. So when we graph this, the x-axis is going to be our angle values, measured in radians. Our y-axis is going to be the sine values. So, and maybe we'll plot a few, we'll even make a little table here just to make life a little bit easier. So I'm not going to pick, and this is where I feel like things get confusing. So just let me point out how this could be confusing if we weren't careful. The x and y I'm using here aren't cosine and sine. X is the angle, y is the sine. This is unfortunate, but just kind of the way things work. So x, the angles I'm going to use are the nice theta equal to 0, theta equal to pi over 2, pi, 3 pi over 2, and 2 pi. All right, so sine of 0. So if my angle is 0, what's the sine value? Is it 1 or is it 0? 1 or 0? Right. Another way I think about which one is which is it's alphabetical. X comes before Y in the alphabet, and cosine comes before sine, right? If you look at the first letter, C comes before S in the alphabet. So if you're ever not sure which one is which, just remember, oh yeah, it's alphabetical. X before Y, cosine before sine. So X is cosine, Y is sine. So if I want to find sine of pi over 2, it's going to be 1. I should write that's sine of 0. That's sine of pi over 2. Sine of pi is going to be what? Somebody tell me. Thank you. Sine of 3 pi over 2 we already did. It was -1. And finally, we're back to where we started. Sine of 2 pi is equal to 0. And then this thing just repeats. It is what's called a periodic function, meaning after you go through one full period, you just get the same graph. Like you can cut it, move it over, cut it, move it over again and again and again and again. So there's my 2 pi, cut that in half and half and half. 2 pi is about 6-ish. So my graph is not going to be perfectly to scale. That's about 6, but I'm going to draw my 1 like about there. It's because it's hard to draw if you don't. So sine of 0 was 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is -1. Let me zoom in so you can see that better. And finally, sine of 2 pi is back to 0. So here is one period of my sine graph. And it would continue. So then you could take that, cut it, and move it over here. So you could do another period if you really wanted to. Right there's another period doing the same sort of deal. You go to the left as well. Right there, and there, and there, and there. So there's like 3 periods of your sine graph. Times. Okay. The whole reason I've talked about this is really so that I can do the thing I'm about to do, which is say, I want to find the derivative of this function. And there's a way we could use the limit definition, but it requires some trig stuff that we may or may not actually talk about. So I want to show you the nicer way of seeing what the derivative looks like. And of course, do I have enough room here? Maybe, sure. Let's just draw it again. And it's too bad because I really think I did a good job drawing it there. Oh, well, sometimes you have to draw it again. So let's draw sine of x one more time. I can say words. Spacing these out evenly. These are my quadrantal angles, pi over 2, pi, 3 pi over 2, 2 pi. Which are 1, which are -1. And of course, I'm sure this graph is not going to look as good as the one I just drew because, you know, how life goes. If you're drawing a sine or a cosine graph, you should try and make it look fairly smooth. So not too pointy anywhere. Cool, there's my sine graph. All right, here's what I really want you to see. If I try to find the derivative of sine, so I want to find y prime equal to the derivative of sine of x. Well, here's how we graph the derivative. And I know we might not have talked about this really, but one way you can think about taking a function just trying to graph its derivative is by seeing what the slope of the tangent line is. In fact, yeah, let's hold off for a second. We'll come back to this in just a minute, I promise. Let me just look at another example to kind of make this feel a little bit more true to you. Maybe. Let's say I wanted to say, here's my function f of x equal to x squared, which I'm pretty okay at drawing. Sure. You get 0, 0, 1, 1, 2, 4, -1, 1, -2. 1. And now what I'm going to do is I'm going to try it now. Oh, sorry. Well, I'm way zoomed in. I'm like, what's going on? Sorry about that. So what I want to point out is I'm going to try and graph the derivative while pretending like I don't know what the derivative is. So I'm going to graph the derivative. And what I'm going to first look for is some easy things like right there at that bottom, at the vertex there. If I draw a tangent line, it's going to be what kind of tangent line? That's not a good question. Is it going to be a vertical or horizontal line? If I draw the tangent line to that point right there. Totally horizontal. There's my tangent line at the vertex. And a horizontal line has what kind of slope? Right. So right there at that point, the derivative is equal to 0. So okay, so if I'm graphing the derivative at there, the derivative is going to be 0. Okay, how about right there? When x is equal to 1. In fact, let's just do this. Trying to line things up here. So when x is equal to 1, is my tangent line having a positive slope or a negative slope? Definitely positive. And when x is equal to 2, does my tangent line have a more positive slope or a less positive slope? Right. So when x is 1, my slope is positive. And when x is 2, my slope is even more positive. On the other side, when x is -1, my slope is negative. So if I'm graphing the derivative, the value is going to be negative. And when x is -2, slope is even more negative. So my derivative is going to be even more negative. So the y values on your derivative correspond to the slopes on your original function. And then if we try to graph this, again, I already kind of knew what the answer is going to be. We can see that, oh yeah, our derivative looks like it's a straight line. It's probably like 2x, which it is. Okay, let's go back. So the point is, I'm going to do the same sort of thing here. I'm going to look and let's try and line things up here. Be a good time to have a ruler, but I think I left it in my office. I promise you want to see this. Okay, yeah. So let's look right here at pi over 2. I'm at that point right there, and my tangent line is definitely horizontal, meaning the slope is 0, meaning the derivative is 0. And the same is true over here at 3 pi over 2. And over here at 0 is my slope positive or negative? The slope of the tangent line is definitely positive. It's actually pretty much, it's not actually probably, it is +1. If you look at that tangent line there, it really looks a lot like y equals x, and it is. That is a slope of 1. So my y value there, my derivative is 1. And over here at pi, I should point out when I draw these tangent lines, technically the tangent line actually goes through the graph, which can happen sometimes. It's kind of weird, but it happens. The tangent line there, the slope of the tangent line is -1. And finally, back here, while we're back at essentially the same place we started at, the slope of the tangent line there is +1. Now, if we graph this, it's going to look like, if I graph it well, it's going to look like cosine. Because it is cosine. Because the derivative of sine of x is cosine of x. And if you did the same sort of thing again, if you tried to draw the derivative of this using tangents, we could see that you'd have a, of course I didn't leave myself enough room. If you want to find the derivative of cosine, well, the derivative there is going to be 0. The derivative of pi over 2 is going to be -1. The derivative of pi is going to be 0. I'm sorry, -1. Sorry, I plotted that wrong. The derivative of pi is going to be 0. At 3 pi over 2, the slope of the tangent line is +1. Sorry, I'm not labeling things, and I'm kind of going fast here. And then finally, at 2 pi, the slope is 0 once again. So if I graph this, it looks like I took my sine graph and did what with it? You could say that. You're not wrong. But there's another interpretation I would prefer, which is that I took my sine graph and I flipped it over. Right? If you take this graph and you flip it over the x-axis, it looks the same as that. Derivative of cosine is -sine. Cool. So. You are probably gonna talk about this in class tomorrow, derivatives of trig functions. Yeah, I was hoping to get to the product rule, but we didn't really get to the product rule. So what I'll say is what's coming up is the product rule. So the product rule, just so you can see an example of it. We use the product rule for taking the derivative of something like x cubed times sine of x. And the problem here is you cannot just do what we wish we could do. It's not just 3x squared times cosine of x. The derivative of a product is not equal to the product of the derivatives. Instead, I'll show you, and then I'll show you one more example. I know I'm out of time, but give me just an extra minute. Derivative of x cubed times sine of x is going to be 3x squared times sine of x plus x cubed times cosine of x. The product rule you do by taking the derivative of one piece and multiplying by the other piece left alone, adding and then interchanging what you did. You leave the first piece alone, multiply by the second piece. Let me show you a different example that'll make it more believable. What is x to the third times x to the fifth? If I simplify that. X to the how much? 8, right? We add those powers. And the derivative of x to the 8th is 8 times x to the 7th. But if I apply the product rule here, the derivative of something times something else using the product rule, it's going to be the derivative of the first thing times the second thing plus the first thing times the derivative of the second thing. And if we simplify that, we get 3x to the 7th plus 5x to the 7th. And 3 of something plus 5 of something is equal to 8 of that something. Oh, they're the same. And they'll lastly say, and then I promise you can go, it is definitely not equal to 3x squared times 5x to the 4th, which would be 15x to the 6th. That is not the derivative of x to the 8th.